NENOMATICA, where mathematics meets YouTube excellence. Welcome to this video on the binomial square formula. Today we'll learn about the square of a binomial, which is a fundamental algebraic identity used in many areas of mathematics. Let's start by looking at the general formula. The square of a binomial, a plus b, is equal to a squared plus 2ab plus b squared. This is one of the most important algebraic identities that you'll use throughout your mathematical journey. Let's work through an example to see how this formula works in practice. Consider the expression, open parenthesis 2x plus 3y close parenthesis squared. To solve this, we'll substitute a equals 2x and b equals 3y into our formula. Now let's apply the binomial square formula. A squared plus 2ab plus b squared. First, we find a squared, which is 2x squared, which equals 4x squared. Next, we calculate 2ab, which is 2 times 2x times 3y, which equals 12xy. Finally, we find b squared, which is 3y squared, which equals 9y squared. Putting it all together, we get 4x squared plus 12xy plus 9y squared. Let's take a moment to understand this formula geometrically. Imagine a square with side length a plus b. The total area of this square is a plus b squared, but we can also break it down into 4 regions. One region with area a squared, one region with area b squared, and 2 rectangles each with area a times b. So the total area is a squared plus b squared plus 2ab, which matches our formula. Let's look at another example. This time we'll solve, open parenthesis negative 1 plus y squared close parenthesis squared. For this example, we substitute a equals negative 1 and b equals y squared into our formula. Now, we apply the binomial square formula again. First, a squared equals negative 1 squared, which is positive 1. Next, 1 squared, which is positive 1. Next, 2ab equals 2 times negative 1 times y squared, which equals negative 2y squared. Finally, b squared equals y squared squared, which equals y to the 4th power. Putting it all together, we get 1 minus 2y squared plus y to the 4th power. Now, let's work through one more example from our worksheet. Let's solve, open parenthesis xz plus open parenthesis negative y close parenthesis squared. Here, we'll substitute a equals xc and b equals negative y. Let's apply the binomial square formula one more time. First, a squared equals xc squared, which equals x squared z squared. Next, 2ab equals 2 times xz times negative y, which equals negative 2xcy. Finally, b squared equals negative y squared, which equals y squared. Putting it all together, we get x squared z squared. Putting it all together, we get x squared z squared minus 2x z y plus y squared. Let's summarize what we've learned about the binomial square formula. First, the square of a binomial, a plus b squared, equals a squared plus 2ab plus b squared. This formula works for all types of mathematical expressions, including variables, numbers, and more complex terms. We've seen 3 examples, the square of 2x plus 3y, the square of negative 1 plus y squared, and the square of xc minus y. I encourage you to practice with different binomials to master this important formula. Thank you for watching this video on the binomial square formula. Remember that this formula is a powerful tool in algebra that will help you simplify many expressions throughout your mathematical studies. See you in the next video. Formula is a powerful tool in algebra that will help you simplify many expressions throughout your mathematical studies. See you in the next video. Today we'll be exploring perfect square patterns and learning how to recognize and manipulate these expressions efficiently. Let's start by looking at some examples. Let's look at our first example. We have the expression x to the power of 4 plus some missing terms plus 1 over x to the power of 4. Before we solve this, let's recall the perfect square pattern. A perfect square has the form a squared plus 2a plus b squared, which equals the quantity a plus b squared. Let's start by rewriting our expression. We can identify that x to the 4th power is equal to x squared squared. Similarly, 1 over x to the 4th power can be written as 1 over x squared squared. This helps us recognize the pattern more easily. Now we need to find what the missing terms are. If we want to form a perfect square of the form a squared plus 2a plus b squared, we can identify that it equals x squared and b equals 1 over x squared. To complete the perfect square pattern, we need the middle term, which is 2 times a times b. That's 2 times x squared times 1 over x squared. This simplifies to 2. Now we can recognize that this is a perfect square. Using our pattern, a squared plus 2a plus b squared equals the quantity a plus b squared. So our expression equals x squared plus 1 over x squared quantity squared. So our final answer is x squared plus 1 over x squared quantity squared. This means the original expression x to the fourth plus some middle terms plus 1 over x to the fourth equals x squared plus 1 over x squared quantity squared. Let's move on to our second example. We have the expression 9a plus some missing terms plus 4b. We can rewrite 9a as 3 root a quantity squared and 4b as 2 root b quantity squared. This helps us identify the structure of the perfect square pattern. Now, if we want to form a perfect square of the form a squared plus 2a plus b squared, we can identify that it equals 3 root a and b equals 2 root b. To complete the perfect square pattern, we need the middle term, which is 2 times a times b. That's 2 times 3 root a times 2 root b, which equals 12 root a times root b. Using our perfect square pattern, we can rewrite this as 3 root a plus 2 root b quantity squared. So our final answer is the quantity 3 root a plus 2 root b squared. This means the original expression 9a plus some middle terms plus 4b equals 3 root a plus 2 root b quantity squared. Let's summarize what we've learned. When working with algebraic expressions, it's useful to recognize patterns like the perfect square pattern. This allows us to simplify expressions and solve problems more efficiently. For a perfect square, remember the pattern. A squared plus 2a plus b squared equals the quantity a plus b squared. For practice, try to identify other expressions that fit this pattern. And remember, recognizing patterns is a powerful tool in algebra that will help you solve problems more efficiently. Thanks for watching. Welcome to this math lesson, where we'll solve a quadratic equation in 2 variables. Our goal is to find all real values of x and y that satisfy the equation x squared plus y squared plus x times y equals 0. Let's start solving this equation step by step. The first step is to multiply both sides of the equation by 2. We're using the rule that multiplying an equation by a non-zero constant preserves its solutions. We get 2 times x squared plus xy equals 0. This simplifies to 2x squared plus 2 y squared plus 2x, y equals 0. For step 2, we'll rewrite the equation by regrouping and completing the square. We'll use the rule that x plus y squared equals x squared plus 2x, y plus y squared. Let's rearrange our terms. We have 2x squared plus 2, y squared plus 2xy. This can be rewritten as the sum of x squared plus 2x, y plus y squared, plus x squared plus y squared. The first group is exactly the formula for x plus y squared, so we get x plus y squared plus x squared plus y squared equals 0. For step 3, we'll use the principle that squares of real numbers are always non-negative. A sum of squares equals 0 only when each square equals 0. Looking at our equation, we have a sum of squares x plus y squared plus x squared plus y squared equals 0. Since each term is a square, and the sum equals 0, each term must be 0. So we have 3 conditions: x plus y equals 0, x equals 0, and y equals 0. Now we're ready for step 4, to conclude our solution. When we have a system of equations, we need to find values that satisfy all the conditions simultaneously. From our system, we have x equals 0 and y equals 0. Let's verify this solution. Let's start with our problem. If 25 raised to the power of x plus 25 raised to the power of negative x equals 14, find the value of 5 raised to the power of x plus 5 raised to the power of negative x. Let's approach this step by step. Our first step is to make a substitution to simplify our work. We'll define a as 5 raised to the power of x plus 5 raised to the power of negative x. This is exactly the expression we're looking for. For our second step, we'll square both sides of our equation. This is a common technique when dealing with expressions that have a similar structure to the one we're given. So we get a squared equals the square of the entire expression 5 raised to the power of x plus 5 raised to the power of negative x. For our third step, We'll use the binomial expansion formula to expand the squared expression. When we square a binomial in the form of a plus b, we get a squared plus 2ab plus b squared. So a squared equals 5 to the power of x squared, plus 2 times 5 to the power of x times 5 to the power of negative x, plus 5 to the power of negative x squared. We can simplify the middle term. 5 to the power of x times 5 to the power of negative x equals 5 to the power of 0, which equals 1. So 2 times that equals 2. We also know that 5 to the power of x squared equals 5 to the power of 2x, and 5 to the power of negative x squared equals 5 to the power of negative 2x. So a squared equals 5 to the power of 2x plus 2 plus 5 to the power of negative 2x. For our fourth step, we'll make a connection to our original equation. Notice that 5 to the power of 2x can be written as 25 to the power of x. Similarly, 5 to the power of negative 2x can be written as 25 to the power of negative x. Looking back at our original equation, we were told that 25 to the power of x plus 25 to the power of negative x equals 14. So we can substitute this value of 14 into our expansion. A squared equals 14 plus 2, which equals 16. For our fifth and final step, we'll solve for a by taking the square root of both sides. A squared equals 16, so a equals plus or minus 4. But we need to determine which value to use. Since a equals 5 to the power of x plus 5 to the power of negative x, and we know that any number raised to any power is always positive, both terms in our expression are positive. So their sum, which is a, must also be positive. Therefore, a equals positive 4. So we found that 5 to the power of x plus 5 to the power of negative x equals 4. Let's summarize what we've learned. We started with the equation 25 to the power of x plus 25 to the power of negative x equals 14, and we needed to find the value of 5 to the power of x plus 5 to the power of negative x. We used substitution, binomial expansion, and properties of exponents to transform the problem. The key insight was recognizing that 25 to the power of x is the same as 5 to the power of 2x. Through our step-by-step approach, we determined that 5 to the power of x plus 5 to the power of negative x equals 4. Try practicing similar problems with different bases and exponents to strengthen your understanding of these techniques. Thank you for watching this video on solving exponential equations. Remember, the key to mastering these problems is understanding the properties of exponents and recognizing patterns. Keep practicing, and you'll become more confident in solving these types of problems. Let's look at the problem we need to solve. We are given that a squared equals a plus 3, and we need to prove that a to the fifth power equals 19 a plus 21. Let's start our proof step by step. First, we'll rewrite a to the fifth power as a times a to the fourth power. Next, we can express a to the fourth power as a squared squared. This will let us use our given equation. Now we can substitute our given equation. Since we know that a squared equals a plus 3, we can replace a squared in our expression. Next, we need to expand the expression a plus 3 squared. This will give us a squared plus 6 a plus 9. Then we multiply everything by a. Now we need to replace a cubed and a squared with expressions involving only a to the first power. First, a cubed equals a times a squared, which is a times a plus 3, giving us a squared plus 3a. Then, we replace the a squared term with a plus 3. Finally, we substitute a squared equals a plus 3 one more time. This gives us a plus 3 plus 18 a plus 18, which simplifies to 19 a plus 21. And with that, we've proven that a to the fifth power equals 19 a plus 21. Let's summarize what we did in this proof. First, we rewrote a to the fifth power using index laws. Then we used our given equation, a squared equals a plus 3, to substitute and simplify. We carefully expanded expressions and combined like terms at each step. This type of algebraic manipulation is common in many areas of mathematics. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.